Hello, I'm Maryam from Penn State University, and in this video, I'm presenting our work on agents that learn board games through multimodal communication. This work is mainly motivated because agents that learn through communications are very adaptable, and because these agents learn from humans, they can be better partners in any activities. We use games as testbed because games can be represented in a very abstract form, and because games vary in complexity. And because dialogue partners can be very different, in particular in terms of information they offer, we design agents that are sensitive to dialogue partners. To cover the background work, the current work on human-robot that learns through communication usually involves human telling robot what to do, so the burden is usually on human. And also these approaches are not MDP-based, and the focus is mainly on grounding or communicating procedures or concepts. In current POMDP-based dialogue systems, the actions are usually happening in a virtual world, and although these systems scale very well, and there is a strong foundation in task-oriented based dialogue systems, the communicative actions are usually limited, and the goal is defined in a very fixed way, and these systems usually don't adapt to different users. So we extend an agent that is trained offline through reinforcement learning, and the agent can learn Connect 4, Goblet, and Corto, but this talk is mainly focused on Corto, the most complex game among the three. The agent can learn both from visual demonstrations and by asking verbal questions, and it is sensitive to how helpful or informative the dialogue partner is. As for knowledge, we represent the knowledge using extensive form game trees, and the agent goal is defined in terms of adding win conditions to the game tree. So before having any dialogue, the agent has no knowledge about the game, but only knows how to add new win conditions to this game tree. After having the dialogue, the agent ends up with a partially or fully complete game tree, and the agent aims to learn as much as possible about a game. For the experiments, we asked a few questions, but among them is, our dialogue policies are actually different with respect to different users? Is the acquired knowledge is different with respect to different users? How well the agent can play after having the dialogue? And how well the agent can perform when having conversations with humans? We've designed a simulated dialogue partner that uses a meaning representation language to communicate with the agent. And one of the benefits of having a simulated DP is efficient training, but another benefit is having full control over it. So we've designed a DP that its informativeness ranges from 0% to 100%, and this can affect different types of questions in different ways. For example, for questions of type confirm, the agent will, a DP with X% informativeness rate would respond with unknown X% of the time. But for questions that are type request, a DP that's X% informative would provide only X% of the full information. For example, given board D3 and having the question, let's step back to the third example for a moment. Where else can I move the pieces and still win? A fully informative DP would respond with column 0, column 1, and column 2, but a less informative DP would respond with column 2. As for agent, it has a hierarchical policy which enables it to switch context among different visual demonstrations. And also it is fed by a reward that is a function of number of ways to win, a function of strategic value, which is computed by game tree knowledge reasoner to ensure that the agent is learning high quality win conditions as well. And also to ensure efficient questioning, the reward has the turn cost C as well. The belief space, which is also hierarchical, has two types of belief in it, confirmed belief and inferred belief. The confirmed belief is the type of knowledge that is learned directly from the DP. And inferred belief is a type of knowledge that is derived by game knowledge reasoner based on the existing knowledge in the game tree. In the first experiment, we wanted to see how the policies are different across different levels of informativeness rate. So we trained agents under 6 different conditions for 10K epochs, and then we looked at the frequency of communicative actions at the end. So the table shows the frequency for the global policy on the top and for the local policy at the bottom. And one of the things that we can see here is that the agent tends to ask more WH questions, where the DP is more informative, and more yes or no questions when the DP is less informative. Next, we wanted to see how the agent can learn and play. So to do that, we trained agents under 3 different informativeness rates of 100, 50, and 20. And then we paired each agent with a matched DP and an unmatched DP, ending up with 5 different combinations. We ran each agent 10 times and then sampled 1 final belief randomly. We recruited 28 subjects to have to play with these agents twice each, and then the agent was using minimax game playing to play. So the table shows the knowledge and the outcome of the game. And what we can see here is that as the informativeness rate decreases, the agent is learning less and it's also winning less. But more interestingly, the agent is doing better when it's given a matched dialogue partner. Next, we wanted to see how the agent can have a conversation with a human. And to do that, we needed training data for NLG and NLU. So we trained 13 college students and taught them the MRL, and then asked them to translate the MRL to natural language for us. We, at the end of this, we had 960 dialogues, and using this training data, we trained NLG and NLU, and then we had an agent that was trained with 100% informative dialogue partner to have conversations with 18 subjects that we recruited. And then we asked subjects to fill out a questionnaire for us. So the table shows the final knowledge after this experiment. And then for the NLG fluency rate, the subjects rated it above average. The NLU accuracy was 60%. Subjects were 100% informative only 41% of times. That was an interesting result of this experiment. And in terms of their experience, 11 subjects said that they would be willing to have more conversations with this agent. 1 was neutral and 6 were somewhat dissatisfied. And 14 subjects said that they understood the agent most of the time. So the main takeaway from this experiment is that the dialogue partners directly affect the behavior of the agent and the amount of knowledge that the agent is learning. And so agents are learning the best and the most from matched dialogue partner. So it matters to know that dialogue partners vary. Also, our experiments show that the agent was able to have conversations with human as well without any ability to clarify any confusions during the dialogue, which shows promise for reinforcement learning of dialogue policies that are trained offline in simulation. As for future work, we will look into ways that to incorporate the uncertainty in the user response, and also we will look to see how we can close the reality gap between offline training and also testing it in real-world dialogues with humans. Thank you for watching this video, and I'd be happy to take any questions during QA sessions.